When we talk about trig transformations, we're talking about a transformation just like we would talk about with any other graph. Now in this case we're talking about our three trig functions, which are going to be sine, cosine, and tangent. As you can see, the graphs are displayed below with the noticeable comparison between sine and cosine. You can see obviously that sine and cosine are very much related. The only difference would be, as we were talking in class, we have a phase shift of 90 degrees. So if we would shift sine over and start here, we would see that it's going to actually be a replica graph. And then tangent, of course, is its own monster, where we've got vertical asymptotes where in both the positive and negative y direction, your tangent will be approaching infinity. This happens because we get a situation where we have a 0 in the denominator. Anytime we've got a 0 in the denominator, we get what's called an asymptote in terms of a graph. So we've got our basic graph functions. What we're going to talk about are our transformations. And the transformations are very similar to any other transformation that you would see in any other function. In this case, we've got four basic transformations. The first transformation is going to be the amplitude. So in the last example, we saw sine and cosine. They are sinusoids. They are waves that continue to repeat over and over again. The amplitude of a wave is going to be the peak to the middle, or the valley to the middle. The highest point and the lowest point to the middle of that function. And now in this case, we're going to be talking about the sine function. So if I write the sine function in terms of this function up here, where I've got my function a times my function b of t minus c plus d, I will rewrite it for my sine function. I will write it in terms of a, which is going to be a 1. So my amplitude is going to be a 1. I've got sine of my b value is a 1 as well. Because remember, that 1 is inherently there. We don't always see it. Doesn't mean it's not there. So my b value is 1. My b value is going to be the frequency. So how frequent does this wave occur? And when we're talking about frequency, we're talking about in the range of 0 to 2 pi, or 1 complete rotation. Because remember, with our unit circle, 1 complete rotation was 360 degrees, or 2 pi. So we're talking about how many times this wavelength occurs from 0 to 2 pi. That is my b value. That is what is called my frequency. Now, you'll notice there is no frequency listed on this graph. It's because we don't talk about frequency. What we talk about is the period. The period is how long does it take my graph to complete one complete wave. And we can see here from peak to peak is going to be one complete wave. So from peak to peak, it takes 2 pi, or 1 complete rotation. If I look here to find that, I take 2 pi, to find my period, what I can do is I take 2 pi, which is my 1 complete rotation, and I divide that by my b value, which is my frequency. 2 pi divided by 1 is just going to give me 2 pi, which gives me my period of 2 pi for a sine or a cosine function. So I've got my first two taken care of. I've got amplitude, I've got period. Remember, amplitude is the distance between that middle section and the max, and the middle section and the bottom. So any high or low point in the middle section of that graph. And the period is how often that graph occurs from 0 to 2 pi. The other thing I can look at then is a phase shift. In this graph, we don't have a phase shift. We're just talking about sine. There is no phase shift. So that means that our sine is going to start at 0, 0. Since there is no phase shift, we don't have to worry about c over b, but we will see an example to find your phase shift, you take your C value, you divide it by B. That tells you how much your function is moved either to the left or the right. The one thing to realize, this is a negative sign, which is going to completely switch out everything that you would think. So if my phase shift, let's say for example, let's say I had the sine of x plus pi. Everything mathematically would make us think, yes, that plus pi, move it to the right. It's the opposite. So if it's a plus pi, we're actually going to move it to the left. If it's a minus pi, we're going to move it to the right. That's something that you'll get used to. That's something you'll have to remember. And then my last thing to account for here is going to be my vertical shift. In this specific example, I do not have a vertical shift. I'm not adding anything to the end of this function, so my my equilibrium there, my middle ground, is just going to stay at 0. If it was a 3, or a 2, I would shift it up to 2, and then I would do my function from there. So that's what our vertical shift is. So we've got 4 different things. We've got an amplitude, which is going to tell us how much that graph is stretched or compressed in the y direction. We've got a period, which tells us how long it takes for one wavelength to occur. We've got a phase shift, which tells us if the graph is moved right or left at all, almost like a horizontal shift. And then we have a vertical shift, which tells us where our equilibrium, or that middle point of our graph, is located at in the y-axis. So let's see if we've got an example. Yeah, let's work through an example here. It's a pretty good example. Easiest thing to find is the amplitude. The amplitude, remember, if I'm writing this, I have A times whatever my function is, B of t minus C plus D. My A value is going to be my amplitude. My amplitude is whatever I'm multiplying this function by. This A value is going to be a 3. Next up is my period. To find the period, I have to find what my frequency is. Frequency is represented by B. My frequency in this case is just a 1, so I have 1x. To find my period, I do 2 pi divided by B. So I'll do 2 pi over 1, which is just going to give me 2 pi. So I've got a period of 2 pi, which means from 0 to 2 pi, one wave should be completed. Now if I want to look at my phase shift, I look up here at my C value. Remember, my phase shift is going to be C divided by B. This one will be an easy one. My C value is going to be, we see it's negative, so it's going to be to the right. C is pi, B is 1, so my phase shift is going to be to the right pi. Okay, and then the last thing I have here is my vertical shift, which is going to be my D. Anything I'm adding or subtracting from the entire function, I can see here right at the end I've got a minus 2, so that's going to shift everything down 2 spots. Alright, so it's going to take everything, and in the y direction, it's just going to shift it downward. So if we look at this, if we actually want to express this, we want to draw this out. I've said the easiest thing to do is make your phase shift your new y-intercept, because we have some key features. Once we find what those key features are, we can kind of work with it, figure that out. So we're going to work with pi because we're transferring this over pi to the right, and I'm going to actually label my graph here. We'll go by 90 degrees, or we'll go by pi. 3 pi for 2, 2 pi, that should give us enough room. We've got our 0 location, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, I'll use a different color. Hopefully it doesn't get too ugly. First thing I want to look at, like I said, let's just account for that. Let's move our y-axis over right now. We'll set it at this pi location. So now I don't have to worry about shifting things over, getting confused. I'm just going to start from that dotted line. And let's go with some light blue. So at my y-intercept for my sine, anytime I'm working with my sine function, when sine is 0, my function is equal to 0. So now that's not going to have any effect with the amplitude, but that vertical shift we have to account for. So typically my sine would be right here at this 0 location, but remember, I shifted it over pi and I shifted it down 2. So really I've got a new x-axis, I've got a new y-axis. So when I go to graph this, I'm going to start my new 0 location. And my new 0 location is going to be right here. Over pi, down 2. That's where I'm starting my function. Now we'll go to the right. We know that from 0 to 2 pi, one complete wave will occur. So 0 to 2 pi, one complete wave will occur. So if I'm going from pi, that means from pi to 3 pi, one complete wave will occur. So I'm going to extend this on so that in the right direction, I've got some room here to finish. So we'll go here. We'll put in a 3 pi. We'll put in a 3 pi here. And this one would have to be 5 pi over 2. What I did now is I allowed for us to account for that 2 pi of that period. So from here, I should go up, cross over down, and I'm going to finish off right here at 3 pi. So I should complete one wave between these two yellow dots. So if I'm going to complete one full wave from those yellow dots, I know that in half of that distance, I'm going to complete half of a wave. And I know in half of this distance, I'm going to complete a quarter of a wave. So from this yellow dot to this yellow dot, I'm going to hit my max. And remember, my max is going to be whatever my equilibrium point is, which is -2, plus my amplitude, which is 3. So I'm going to have a positive 1 as my maximum, which is going to be right in there. Now the same thing from 2 pi to 3 pi. I've got to complete that wave. I'm going to hit a minimum. So my minimum is going to be that same thing, that equilibrium point, which is -2, and now minus 3, which is going to give me a -5. So minus 2, minus 3, minus 4, minus 5. And it's going to be right about here. So now I've got my key features, is what we call them. I like to put wherever I'm starting, and then a couple different points, and then it makes it easy to just go through. And I can completely graph one cycle of this. Now I could go back the other way, and I do the same thing. I know at each of these locations, I should have a different value that I'm hitting, and we'll see this function's just going to continue on in this sinusoid pattern. So it's going to continue on as a sinusoid for really the rest of this function's existence.